with us, which will give this public lecture about random rubber bands.
Okay. Thanks. Okay. So, can I just have a show of hands? So, who is not a probabilist, sort of slash stochastic analyst, whatever, in the audience? Okay, so that's a reasonable fraction, just as well. Good. Right. So so the aim of the talk is, first maybe I should say this is based on joint work with Yvan Brunet, who is probably sitting somewhere here, and Frank Gabriel and Lorenzo Zambotti from Paris. And so the aim was actually to build, if you want, the natural evolution on strings in a manifold. Okay, so you take a map from the circle into a manifold. It doesn't have to be injective, so the thing is sort of allowed to cross itself. And you want to build a natural evolution on these. Okay, so the thing is supposed to sort of wobble around in some random way, and you want the most natural way of wobbling around in a manifold for a string. And so maybe before I get to that, I should explain for the non-stochastic analysts in the audience what would be already the most natural way for a point to wobble around on a manifold, right? Before we actually get to loops wobbling around. So you could do the following thing, right? You take, let me see if there's some chalk here. Yeah. Okay, so you've got a Riemannian manifold, so you have your right, so you've got something like this. It doesn't have to be two-dimensional, it can be any dimension. And you have a point somewhere on that manifold. And now you want to figure out sort of a natural way of making this point move randomly around in that manifold, right? So there's one natural way, one non-random way, which is very natural to move around in a manifold, which is to pick a direction and then just follow the geodesic in that direction, right? So that's the natural non-random way of moving around. So what could you do? Well, you can pick a random direction, right? And so the way you pick a random direction is, well, the tangent space, since it's a Riemannian manifold, the tangent space has a norm on it, okay? It has a scalar product on it. And so there's a natural way of identifying it with sort of Rn, and then you just take a point on the sphere, for example, right? So you take the unit sphere, and then you move that forward onto your tangent space. So that gives you a random, so you take a point at random on the unit sphere, that gives you now a random direction on your manifold, in the tangent space of your manifold. And then what you do is you move in this random direction, but you move only a very short bit. Right, so you move a very short bit, and then you stop and you pick another direction at random starting from here. You move a short bit, then you pick another random direction, you move a short bit, and so on. And then, of course, this is not very natural because here I have to tell you sort of how far you go, right? And so what you would want to say is you want to take the limit where you sort of move by 0 every time, right? And the correct way of taking that limit is something like, well, you actually move by root epsilon, and the correct way of scaling time is to say that actually you do that in time epsilon. So you go at actually pretty high speed, so you go at speed sort of 1 over root epsilon. You move around on your manifold like this, and you send epsilon to 0, and if there's a limit for that guy, well, that would be a pretty natural way of moving around on the manifold. And so what you get is something like that, right? So here the manifold would be the 2-sphere, and, well, you know, you started at some point. So here I conditioned it to actually eventually come back where it started, and you get something like this, right? So it sort of wobbles around in a pretty rough way, and then eventually comes back where it started. And you can show that, it doesn't really depend too much on the details of how you do that here, right? I mean, in the sense that if instead of picking a direction by choosing a point sort of uniformly on the sphere and then moving it forward with in an isometric way into the tangent space of your manifold, you could have picked your point according to basically any radially symmetric distribution. Right? You pick any radially symmetric distribution as long as it doesn't have too heavy tails, and you do the same construction. It gives you the same guy in the limit. Okay, modulo there's a time scaling, right? But modulo or time scaling, you always get the same guy in the limit. Okay, so there's really only one natural object that you can get in the limit. And so if you wanted to describe this object in local coordinates, if you put yourself in some kind of coordinate patch here, and you want to describe what's going on, there are two natural ways in stochastic analysis of describing processes like this. So in local coordinates, this is given by what's called the stochastic differential equation. And so a stochastic differential equation is like a normal differential equation. So a normal differential equation would be something like this, right? dx by dt is equal to some right-hand side, which is a function of x. But here you have terms like these dw's, and well, the way you can think of this as just saying, an ordinary differential equation, you can interpret this as being some kind of very small, but infinitesimally small in the limit, but you can think of it as being some very small time increment, and then you say, well, over that little time increment, my position moves by this amount times the length of the time increment, right? And then you take time increment to 0 and you sort of move along like this, and there will be some sort of Euler scheme, and the limit is the solution to your differential equation. So here you do the same thing, but instead of just moving by a deterministic amount, you also move by a random amount. And what this dw here means is basically, well, in that little time t, or dt, you move by this amount here times a random amount which is Gaussian with variance dt. Okay, and so a Gaussian with variance dt moves by typically about square root of dt. Okay, so this thing sort of moves by a random amount which is about square root of dt. And then you can show that if these coefficients are kind of smooth, then you can take limits and you get a limiting process. And the point here is that if you write it in local coordinates, you would somehow like to write something like this, just this term here, right? Because you would say, these sigmas are just a bunch of vector fields, so that the sum of the sigma squares is the metric or the inverse metric of your Riemannian manifold. And so what this really says is that you move by a little amount which is a Gaussian that has a covariance which is proportional to the metric tensor. So the covariance matrix of this little Gaussian is basically dt times the inverse metric tensor. Right? And that's kind of what you would like to say you're doing, because picking a point sort of uniformly on the sphere, or say in a Gaussian way in Rn, and then moving it forward in an isometric way onto the tangent space of the manifold, gives you precisely a Gaussian with covariance matrix, the inverse of the metric tensor. And then you say, well, if you look at what happens sort of infinitesimally, things are pretty much flat, and so geodesics are basically just straight lines, right? And that means that that picture should kind of correspond to this. But the point is, if you want to get the correct process, you have to add a correction term like this. So here these gammas are the Christoffel symbols for your manifold. You have to add a correction term like this. And the reason why you have to add these correction terms is because, well, as already mentioned, this guy makes you move by about square root dt. in every little time interval. And so, you know, if you deform things, you don't have to just look at what happens. You don't have to just look at the Jacobian, if you want, of the deformation, but you also have to look at the second derivative, because the second derivative would give you sort of corrections that are of the order of the square of this guy. And if this were a dt square, then you can forget about it. But a dw square is of size about dt, because the dw is of size about square root dt, and so you can't forget about it, right? And so this sort of reflects the fact that, you know, things aren't quite flat, and so geodesics aren't quite straight locally, and the second order effect actually still shows up, basically because of this square root dt here, right? And there's actually a different way of writing it. So this is called the Ito. Well, so Ito integral basically means at every instant of time you sort of pick a random variable which has the correct covariance, you move in that direction, and then you iterate and you take limits of that. Stratonovich would be the procedure where you say, well, these guys are really increments of one-dimensional Brownian motions, and then I can approximate Brownian motions by something smooth, and then I can interpret this as an ordinary differential equation where this product is just a normal product and this guy becomes just the derivative of that smooth approximation, okay? And then I can try to take limits. And when you do that, you don't get the same limit as when you do these type of approximations that I mentioned earlier. And so when you do this, in order to get the same process, you have to add a different correction term. Okay, so depending on how you interpret your solution, you have to add different correction terms in order to actually get the same process in the limit here. Okay, and the process is sort of well defined. So it's this Brownian motion, which if you ever follow the course on Markov processes, it's the Markov process with generator being the Laplace-Beltrami operator of the manifold. Okay? But the point here is that for these stochastic differential equations, you have two different ways of interpreting them, which is the Ito way and the Stratonovich way. And they are different, and they have different properties. So the nice property of the Stratonovich way of interpreting differential equations, stochastic differential equations, is that it obeys the usual rules of calculus, because it's just obtained as limits of ordinary differential equations, and they obey the usual rules of calculus. And so in particular, you see that, you know, the guy that we want to describe in the limit is a geometric object, and so you only have geometric quantities that arise on the right-hand side, right? These guys are vector fields. That's a covariant derivative, so this guy is again a vector field, so you just have vector fields on the right-hand side. Whereas here, even though the sort of indices contract in the right way, this guy is a Christoffel symbol, so it's not a 2-1 tensor. So, and so this doesn't actually transform like a vector field, right? So this Ito way of writing things doesn't obey the usual rules of calculus. So the change of variables formula has to be replaced by Ito formula, which is different. But it has a nice property, which is that here you really have this interpretation which says that, you know, infinitesimally you kind of move by a random quantity which is a Gaussian with this covariance. So in particular, the law of this guy doesn't depend on the particular choice of the sigmas. It only depends on, you know, the sum over I of sigma I transpose, if you want, right? So it only depends on this covariance matrix, whereas this guy here in general depends on the choice of the sigma i's, right? So you have two different ways of interpreting things, and both have their own nice properties, but there's no way of interpreting it that has both of these nice properties, if you want, right? So, okay, so now let's go up sort of one dimension. Okay, so now what we want to do is we want to think about, instead of having a point that sort of wobbles around on this manifold, you take a rubber band, so a loop. Right, so that guy is just a map, if you want, from S1 into your manifold. And so now you want to build the most natural evolution on these guys, right? And so again, you have to start from, well, so what's the most natural deterministic evolution on these guys first, right? And a natural deterministic evolution on these guys is, well, if you want, sort of the analog of the heat equation. So it's the thing that tends to turn these guys into closed geodesics, okay? And so how do you turn a guy like this into a closed geodesic? Well, there's a natural energy function on these loops, which is just you go along the loop, and at every point you look at the tangent vector, and then you look at the square of the length of that tangent vector, but the intrinsic length, you know, with respect to the Riemannian metric in the tangent space, and then you integrate that along the loop. And critical points of that energy are just closed geodesics, okay? And so a natural evolution is to just take the gradient flow with respect to that energy, okay? So that's a very natural way of having loops evolve in a deterministic way, which tends to turn them into closed geodesics. Okay? So if you do that, what's happening? This doesn't work. Oh, it closed itself somehow. So you get something like that. Okay, so that's my loop here. And you see it slowly sort of, well, on the sphere, the only closed geodesics are sort of the big circles and points, and the big circles are sort of unstable, so typically it won't converge to one of these unless you start with something which has the right kind of symmetries. And so what it actually wants is it just turns into a small circle that just shrinks to a point eventually, right? So you just see it shrinking. It becomes more and more like a small circle here, and then that circle will actually eventually shrink to a point, but it just takes too long for the, right? But so that's what the this deterministic evolution does. One thing you see is that it has a smoothing effect, right? So at the very beginning, I started out with something that wasn't smooth, right? So there were corners here, and these corners were instantly smoothened out, right? So it immediately becomes smooth. And, well, if you write the gradient flow for this energy in local coordinates, well, you see immediately why it smoothens out, because you get something that looks like a heat equation. Okay, so if you write this in local coordinates, so now x, so there are two coordinates, right? There's t and x. Time was the time in the movie, and x is the coordinate along the loop, right? So x takes values in the circle. So here, that's where x takes values in. And then t is just the time in the movie, right? So it's the evolution time. And so in local coordinates, you just see a heat equation, and then there is this additional term. Well, sometimes you can view it as sort of being there in order to make this expression equivariant under changes of coordinates, right? If you just take the heat equation and you write it in a different coordinate charge, then it's not the heat equation anymore, right? It gets a correction term. Whereas if you write this guy in a different coordinate charge, then it will be again the same guy, just with the Christoffel symbols in the new chart. Okay? So this way of, this equation here has the right kind of invariance. And so that's the natural, if you want, the natural deterministic way of evolving a loop in a Riemannian manifold. And so now, how do you do the natural random way, right? Well, so imagine, so this deterministic way of evolving it, I could interpret it as, you know, I could have approximated it, if you want, in the following way. So instead of having a continuum loop, I can view it as a bunch of beads, right? that are linked together by little springs, okay? And the energy, and these springs, you can view them as just little pieces of geodesic, and then you say the energy of each spring is just proportional to the square of the length of that little geodesic. Okay? And then that's exactly a discretization of the energy functional that I wrote down earlier. And so then this evolution is essentially the evolution that tries to minimize the energy that's stored in these springs, right? So of the potential energy of the springs. And so now imagine you have that discretization, so you have these beads that are kind of connected to each other by little springs. They want to do this deterministic evolution, which is try to minimize the potential energy, the total potential energy stored in these springs. And now, well, the natural way of making it random is to essentially do the same thing as before, but for each of these beads independently. Right? So for each of these beads, well, you want to add a random bit, which just pushes it around sort of randomly in a way which is compatible, with the Riemannian metric at the corresponding point, and which is independent for each bead. Right? So that, if you want, is a relatively canonical thing to do. But of course, you would like to know, well, that this canonical thing to do actually doesn't, right? I mean, here I took a somewhat arbitrary way of approximating that continuum guy. And then I said, well, on this particular way of approximating it, there is this sort of natural way of adding randomness to it. Maybe I could approximate it in a slightly different way, and there would be a slightly different natural way of adding randomness. You would like to know that there is some kind of, uniqueness of the guy that you get, right? In some sense. But, okay, so if we write these guys, if we try to take at least formally some sort of continuum limit, right? So we want to send this epsilon to 0, get some kind of continuum limit. That at least formally you would want to write down the following equation. So this is just this guy here, this Laplacian with a second bar here, is just a shorthand for the deterministic part of the evolution, right? So that was heat equation plus Christoffel symbols times kind of two products of the derivative of the solution. So that's just shorthand for that. And what you'd like to do is now you do sort of the same thing as before, right? Is you choose a bunch of vector fields that generate the metric, in the sense that sum of sigma I square is your inverse metric tensor. And then you just add independent noises, but this time, so before these noises were just, if you want, derivatives of Brownian motion, so they were just white noises in time. Now these guys depend both on time and space. Okay, so the natural thing here is to have a noises which are in some sense independent, not just independent at any instant of time, but also independent at every point in space. So formally what you want to do here is to put something Gaussian which has a covariance which is just delta function both in space and in time. And I suppose there's a delta ij missing here, so the different components are also independent. Right? And so then the question is, well, so first, is there a guy like that, right? So is there a natural way of defining this object? Or for example, if I did the discretization that I showed on the previous slide, how strong do I have to make the noise so that these guys actually have a non-trivial limit, right? I mean, here there was you had to choose the scaling right, in the previous picture, which was that in time epsilon, you had to move by about square root of epsilon in order to get a limit, right? And this exponent a half was sort of crucial to get a limit. If you choose it differently, you don't get a limit. And so it's not clear a priori what the correct sort of exponents are here. And then before we also saw that, well, if you write things in local coordinates, there are actually different ways of interpreting things. And depending on how you interpreted it, you actually needed to add a correction term and the correction term you needed to add actually depended on the interpretation. Right? And so there might be something similar going on here. Right? And the problem here, which to some extent already arises in the simple case of just one point moving around, but it's a much milder problem there. So one problem is that you expect the solution to be extremely irregular. Right? So actually I can show you, let me show you a movie. And again, that guy kind of got disappeared, so I have to. Right? So that's the kind of thing you get. Right? So here, well, so I did exactly that discrete sort of algorithm, if you want, with the correct scalings in epsilon. And what you see is that, well, so first, at every instant of time, this thing kind of looks like what I had before, right? In the sense that at a fixed instant of time, this guy looked a little bit like this Brownian motion on the manifold that was conditioned to go back to itself. Right? But then it moves around, and it moves around in a pretty, I mean, you see the motion, sort of the time motion, seems to be in some sense even less regular than the space motion. Okay, so it's maybe sort of difficult to compare sort of time evolution to space evolution sort of by looking at it on the movie. But you can quantify that, okay? So and it is the case that somehow the time evolution of this guy is actually much less regular than the spatial behavior, if you want. So let's go back. Okay. So one thing you could do, right, is to do, remember in the simple case of just a point moving around, I mentioned that when you write things in local coordinates, you can write down some equation, and there are these two ways of interpreting it. And the second way, the Stratonovich way, was to say I actually interpret it still as a limit of ordinary differential equations, where I just replace the noise by something smoothened out, and then I take the limit. So you could try to do something similar. Right? So here what you would want to do is you would want to replace these guys by something which has a covariance which is no longer a delta function, but just some kind of smoothened out version of a delta function. And here it turns out that it's sort of a good idea to choose the length scales to be sort of epsilon in space and epsilon square in time, because that's sort of compatible with the scaling of the heat equation, right? In the heat equation, you have a dt that balances a dx square, and this is the scaling where if you differentiate this in time, you have a 1 over epsilon square coming out, and if you differentiate twice in space, you also got an 1 over epsilon square coming out, right? So this is sort of the natural way of choosing the length scales here. And so you can ask yourself, well, if you look at this, you get a limit. Right? But then, previously, in the case of just a point moving around, we had to actually add a correction term. So maybe you would also have to add a correction term in order to get a limit, or in order to get at least the right limit, okay, whatever the right limit means. So here it turns out, so the theorem is that there is a limit, okay, so you don't, without adding any correction term, you do actually get a limit when you send epsilon to 0, but you don't have uniqueness. Okay? So depending on how you approximate your delta function, so depending on the shape, if you want, of that function rho here, you would get different limits. And if you choose the sigma i's so that this constraint is satisfied, so in the previous case, that constraint actually killed the correction term where you did the sort of Stratonovich approximation, right? So it sounds like a good constraint to impose, because at least in the case of the point moving around, that would actually kill the correction term. Okay? So, and you can always impose that. I mean, so for any manifold, you can always find a bunch of vector fields, so this is true, and that implies this constraint. So the theorem here is you get a limit, but the limit is not unique in general. And, well, okay, so the theorem here is that really you can, in principle, you can get an 8-dimensional space of possible limits, okay? Which is, you know, it sounds like pretty bad non-uniqueness, but in some sense it's not that bad, right? Because this is an infinite dimensional object. I mean, it's, you know, it's a random process with values in that space of loops, which is a pretty big infinite dimensional space. So you have like an, okay, 8-dimensional subset in that infinite dimensional space, so that if you let epsilon go to 0, you always end up somewhere on that 8-dimensional thing, okay? But in general, you do really end up somewhere at different, you do really get different limits. And so then you would like, you know, to ask yourself, is one of these points in that 8-dimensional thing more special than the others, right? So, well, so first maybe just a remark on the general case. So here that theorem took as an assumption that this constraint is satisfied, and it also took as an assumption that the you know, the Christoffel symbols are really the Christoffel symbols for the Riemannian metric, which is given by these sigmas. Okay, so there's a kind of nonlinear relation, if you want, between these gammas and the sigmas, which, you know, were used as an input into that theorem. So you could ask yourself, so what if you forget about geometry, you just write down the equation in local coordinates, you know, you view it in Rn or something, and then you ask yourself, is it, you know, I choose an arbitrary bunch of functions gammas and an arbitrary bunch of functions sigmas without any particular relation between them, I can still ask myself, you know, do these things converge to a limit? And so then in general it doesn't converge to a limit, but you have to add some kind of correction terms. Okay, so in general you do have to add some correction terms. So the first one is, well, that term which I forced to be 0 on the previous slide, right? So I killed it. And the second term is a, well, term which I didn't write down explicitly, but which happens to vanish if these guys are the Christoffel symbols for the metric determined by that guy. Okay. And here, so one somewhat marginally interesting remark, if you want, is that, so if you want to get this limit, this constant here depends on, you know, the shape of this row. So this constant here doesn't depend on anything. Okay? So that's always the same. So whatever the shape of the row, you always get the same constant, and that's also a general thing in probabilities, that constants in front of logs tend to depend less on details than constants in front of powers. So it's an instance of that kind of general meta theorem. So, okay, so in general you have to add these correction terms if you want to get some limit. And then also in general, the possible limits that you get is actually 14-dimensional. Okay, so in general there's a kind of 14-dimensional space of possible limits which depend on the shape of that function row. Okay, so there's now the question of uniqueness, right? So on the one hand, there's the fact that different rows give you different limits. On the other hand, there's also the fact that different choices of the sigmas might give you different limits. Okay, so here the statement was for one specific, right? So it's like for any given specific choice of the sigmas, there is this sort of 8-dimensional family of possible limits. That theorem didn't say anything about whether if you change into a different choice of sigma, whether you actually get the same 8-dimensional space of limits or a different 8-dimensional space of limits. Right? So it might also depend on the choice of sigmas. So the theorem is of that 8-dimensional family, well, there's exactly one element in that family. So it's not a one-dimensional family, so it's one point. Okay, so there's really one notion of solution which does not actually depend on the choice of the sigmas. Okay, and so then that's your candidate, if you want, for the solution, right? So in the general, so that again relies on the sort of geometry. So it relies on the gammas being the Christoffel symbols for the metric of the sigmas. And again, if you don't impose that, so if you just look at completely general equations like this for arbitrary gammas, arbitrary sigmas, then the statement is that there's a one parameter family of possible solutions, if you want, that has these two properties. So in some sense it has both the properties, right? So in the case of SDEs, the Stratonovich interpretation of SDEs had that property, which is that it transforms according to usual rules of calculus. And the Ito interpretation of SDEs had that property, which is that the law of the solution, if you want, only depends on the covariance of the random bit and not on the actual choice of how to write the covariance as a sum of squares. And here there's a one parameter family of solution theories, and every single one of these solution theories has both properties simultaneously. Okay, so it sort of behaves, if you want, like simultaneously an Ito and a Stratonovich solution. Okay, so in the last 20 minutes, I want to give a little bit of an idea of how to prove such a statement. So there are two bits to it, right? So there's one bit which is, how to show that these things do at all converge to a limit. And then there is the bit about, figuring out how big the space of possible limits is and which guys in that space have nice properties and which guys have less nice properties. Right? So let me first start with the first point. And so the first point, right, the problem is that, you have an equation. So here I just wrote down the equation again in local coordinates. And I wrote a sort of thick, fat, red product for each of the products that are, if you want, classically ill-defined, in the sense that, these psi's here, they're these white noises that have as a covariance a delta function, and so you can view them as so you can't view them as random functions because they are too irregular. You can view them as random distributions, but then as random distributions, while they have a certain regularity or lack of regularity, and then here you're trying to multiply them with a random function because this is, well, the solution to this equation, composed with some nonlinear function. And well, we've seen that the solution to these equations, they are pretty irregular, right? I mean, so if they wobbled around pretty badly, and there are kind of rules that tell you how regular does a function have to be so that there's a canonical way of multiplying it with a distribution of certain regularity, okay? And so basically, the sums of the regularities have to add up to something positive, okay, in the correct way of measuring regularity. And so in that way of measuring regularity, the regularity of this guy here is just below minus 3/2. And the regularity of the solution is just below plus 1/2. And of course, 1/2 minus 3/2, clearly doesn't add up to something positive, right? And so that one's a problem. And then you have similar problems here, which is that, this guy is the derivative of the solution, and the solution is actually not differentiable, so it's only a half-Hilda. So this is a distribution, and here you're trying to multiply two distributions, and you're not allowed to do that. And then even if you could do it, you wouldn't be allowed to multiply by that function, because again, they're not regular enough. Okay, so none of these products kind of make sense. And so then there's this kind of general idea, which is to say, well, I don't want to try to make sense of these products for arbitrary distributions of functions, right? I only need to be able to make sense of it for plausible solutions, for plausible solution candidates for my equation, right? And so, for example, you can argue there's a sort of simple scaling argument that tells you that out of these two terms, if you somehow were able to make sense of them, then this guy should behave more badly than this guy somehow. And so if you want to then, this tells you that if you want to just figure out the local behavior of the solutions, well, that should be similar to the local behavior that you get by completely removing this term here. And then here, well, this sigma of u, it's a pretty irregular function, but at least it's a function, right? It's a continuous function. So a continuous function can, at least to some extent, in some very little small neighborhood of a point, be approximated by simply its value at that point, right? And so then you could say, well, if I want to figure out how the solution looks like in the neighborhood of a point, in a small neighborhood of a point, well, that should be pretty close to what it looks like if I completely remove this term and I replace this guy by simply its constant value at that point, right? That's not unreasonable. And then I just get an inhomogeneous linear equation, so I can solve it. So I just solve the heat equation with the white noise. So this you can always do, even if that guy is a distribution. You can always solve the heat equation with any right-hand side you want. And then the argument I just made sort of suggests that if you look at kind of little oscillations of the solution in the neighborhood of a point, so you look at u at a point minus u of some neighboring point, so you think of xt and ys as being very close together, then this should be pretty well approximated by the corresponding linear combination of the same little oscillations for these guys here, right? Because that's what you would get if you just replace this by 0 and this guy by its constant value, which is this value here, right? And so then the idea is to say that, well, if you know how to define these products for this guy here, then since you expect the solutions to look like these guys, maybe that's enough to actually define these products for a large enough sort of space of candidates, so that then you can find, the solution actually lies in that space. And, well, that's sort of the idea, but it doesn't quite work, so easily, in the sense that, well, this here looks a bit like if you look at this sort of looks like a first-order Taylor expansion, right? If instead of having this sigma, instead of having vi here, I just had y minus x, then this would look precisely like the derivative of u in the sort of x direction, right? And it would look like a first-order Taylor expansion. And so, the idea sort of works, but looking at first-order Taylor expansions is not enough. Okay, so you actually have to look at third-order Taylor expansions. And so you get something along the following lines. So let me sort of introduce a more sort of succinct notation, right? So I do that in the following way. So now instead of writing psi i's for the noise, I just write a little circle, and the operation of solving the heat equation with right-hand side something, I write it as just adding a little line like this. So the line, if you want, is convolution with the heat kernel, right? That's what you get when you solve the heat equation. And then actually the derivative of that appears as well, so I write a thick red line for the operation of convolution with the derivative of the heat kernel. And then I write, if you want, sort of pi for the operation of turning a little symbol into the actual process that it represents. Okay, so it's sort of like for polynomial, that would be the map that turns a polynomial, a sort of abstract polynomial, into its concrete realization. And so here, for example, that v that I had before is now just, well, it was the solution of the heat equation with right-hand side given by one of these noises, which I now just represent as noise convolved with heat kernel, right? And then the pi guy is the one that takes that little picture and spits out the actual process and recentered in the right way, right? So in the previous slide, this guy didn't show up by itself, but it showed up as an increment somehow. right? And so now this identity here, I can write it as a shorthand like that. Okay, so that kind of says my candidate solution around the point looks like the value at that point times the constant function 1 plus sigma of the value at that point times, the corresponding increment of this guy here, right? So that would be like some sort of first order Taylor expansion now. If you go to second order, well, you get something like this. Then if you go to third order, you get, something like this, and you can kind of continue. So there's computation rules that you can figure out that tell you what all these terms should be. It turns out that that's sort of the minimum order that you have to go before you can build some kind of space of candidate solutions out of these things, which has good enough properties that you can actually formulate the equation in that space and solve it. Okay, so you do that, that gives you a solution theory. Okay, so you can just take that as a black box somehow. So there's a way of doing that. But so what the general theory tells you is that, well, it gives you some kind of solution theory, and it gives you some sort of approximation theorem, which tells you that, these solutions are kind of stable under, for example, smoothing out these white noises. But then they're only stable modulo adding, relevant correction terms. Okay, like what we've seen in some of the previous slides, where we saw, in the general case, you had to add this correction term that had a 1 over epsilon and another correction term that had a log epsilon. Okay, so there's a general theory now that tells you, well, you do have some kind of solution theory, but when you want to interpret these solutions as limits of, ordinary solutions of ordinary partial differential equations, then you have to take not the exact equation that you started from, but the equation you started from plus some correction terms. Okay? And there are sort of general formulas that tell you what these correction terms look like, and they come up with some constants. And it turns out that there's basically one constant for each of the sort of little pictures that show up in the right-hand side of the equation. And so, so this now is a sort of quite general theorem that tells you can find a choice of constants so that these things converge, and you can choose them. If you choose them in the right way, you get a limit which actually doesn't depend anymore on any approximation or anything. Okay? So you get a sort of more or less canonical notion of limit. But the problem here is that, well, you have to choose these constants, and in a way, some of these constants might diverge, some of them might not. And of course, if one of these constants, say, diverges like 5 times log epsilon, you can choose it equal to 5 times log epsilon, but you could also choose it equal to 5 log epsilon plus 12. Okay? So you can sort of add finite. They are only sort of well-defined if you want modulo adding finite values, right? So if you add finite values to some of these constants, you still get a limit. Now in this particular case, the number of these terms that shows up is actually pretty big. So you end up with, so you actually end up with like 56 of these terms, right? So it's not just the 8 or 14 that appeared in the previous slides. So you actually have 56 different constants that show up. Some of them diverge like log, some of them diverge like 1 over epsilon, some of them don't diverge. And, well, there's a general theorem that tells you that, you can choose these constants in such a way that you converge to a limit, but you have this sort of 56-dimensional space of possible limits that you can get depending on the finite parts of these constants, if you want. Right? And so now what you have, so now what you'd like to do is you would like to kind of reduce dimensions, right? You'd like to get yourself down to just a one-dimensional family of solutions or a zero-dimensional family of solutions or something, right? Something more canonical than this big 56-dimensional family of solutions. And so here, things are, well, these constants, they are Well, the right-hand side of the corrected equation essentially depends linearly on these constants, right? So each of these constants just gets multiplied by some expression, and that expression somehow involves the gammas and the sigmas and sort of derivatives of them and products of them and so on, right? So there's some kind of polynomial expression, if you want, in these gammas and sigmas that multiplies each of these constants. And so you can view this counter term as a map from, so you have a space, which is the space, that's what I call T. So T would be all formal linear combination of these 56 pictures that show up in the right-hand side, where each of them sort of corresponds to one of the constants. And then you have this epsilon map that sort of gives you the actual terms that get created by each of these constants, right? So this guy depends on the gamma and the sigma, and it sort of spits out the corresponding sort of monomial in derivatives or values of these guys. And so now you have two subspaces here. So on the one hand, there's a sort of geometric subspace, which would be the subspace of those terms so that the thing that this guy spits out actually transforms like a vector field. Okay, so that's the ones that are sort of geometric, if you want. And then there's another subspace, which is the subspace of those terms that have the property that if I replace this sigma, these vector field sigma, by a different choice of vector fields that give me the same metric, then it gives me the same counter term. Okay? So I have two subspaces that sort of correspond to these two sort of symmetries that I would like my solution theory to have. And then there's a subspace both, which is not the intersection of the two, okay? So of course there's also the subspace which is the intersection of the two, but this both one is these terms which has, so it's a much weaker thing. So it's the ones where if you take two choices of vector fields that generate the same metric, and you look at the difference of the corresponding counter terms, that thing transforms like a vector field. So this guy is actually bigger than both of these. Okay, so because you see, if you take a guy in here, then that would already have the property that this is 0. And 0 obviously transforms like a vector field. And if I take a guy in here, then those have the property that each of these guys separately transforms already like a vector field. Right? So this space certainly contains both of these spaces as a subspace, and well, a priori it might be bigger than that. Okay? And if you do exactly the same thing for stochastic differential equations, you can define the analogs of these spaces. Of course, these spaces are just whatever, one-dimensional or something, but they have much smaller dimension. So in the case of stochastic differential equation, that space is strictly larger than the sum of these two spaces. And the point is that here, in the case of these stochastic partial differential equation, that space is actually equal to the sum of these. So in a way, it contains only that guy, and that it contains sort of the minimum of what it has to contain, and it doesn't contain anything more. And in a way, at the end of the day, that's, so I don't really have time to go into the reason why, but at the end of the day, that is really the reason why, at the end of the day, we can actually enforce both symmetries here. Okay, so some ideas of the proof. So the thing is, for the evolution of the loop, so you have these two symmetries you'd like to enforce. And so, of course, one natural way of enforcing a symmetry is to find an approximation which already has the right symmetry, and then show that you don't really lose it when you pass to the limit, right? And so the invariance under, sort of like the property of obeying the usual rules of calculus, so that property, you certainly have it if you simply smoothen out the noises, right? Because then it just becomes an ordinary partial differential equation, and it just it transforms under the ordinary rules of calculus. And so you can look at those types of approximations. Okay, and then you can show that you have a general fact which says that if you look at an approximation like that, and then in order to get limits, you have to add these counter terms. Some of them might diverge. There's a pretty general statement that tells you that it's possible to choose these counter terms in such a way that they also preserves the same symmetry. And then the same is true for the other symmetry, which is the one that says the law of the solution doesn't actually depend on the choice of the sigmas. Okay? And again, for that one, you can find an approximation which has that property. It's a different kind of approximation. So if you just smoothen out the noises, then it doesn't have that property. But you can find a different approximation that does have that property. And then again, you have a theorem that sort of tells you, well, that one you can make it converge to a limit by just adding counter terms which preserve that property. Okay? And so now you get sort of two candidate limits that are a priori different, but at least the first candidate limit has sort of the first symmetry you want to have, and the second candidate limit has the sort of second symmetry that you want to have. And then you exploit the fact that we have this completely general theorem which basically says, oh, you can take pretty much any approximation that you want. There's always a way of choosing the counter terms so that you get a limit, and you can make that limit always the same for all the approximations. And so that means that these two limits that I've obtained, which have the right symmetries, they actually have to differ. They have to be sort of almost the same. So they have to differ by an order 1 counter term, which, you know, when you sort of fiddle around a little bit with the equations, you figure out that that counter term has to be in this space T both somehow, which has this sort of mix of the two properties. And then you exploit the fact that this T both is precisely the sum of these two spaces, and in a way, you know, that's enough to actually create precisely one solution that kind of, where if you want the two sort of spaces of possible solutions intersect. Okay. And okay, so I think I'm exactly 5 o'clock, so that's probably a good point to start. Yeah, so there's a couple of remarks here. So one thing is that, you know, so you start with a nice geometric kind of question, which is sort of build the natural evolution for these strings here on the manifold where there's no local coordinates around, and then you write everything in local coordinates, and you have to work pretty hard because you end up with all sorts of expressions that don't have geometric interpretations anymore. Just in order to, at the end of the day, say, well, actually, we can forget about all that, and we actually find an object which is sort of the same, whatever the coordinate chart you look at it. And so, of course, you would like to have a more intrinsic way of doing that. I don't know, it's not completely... Okay, so at the moment, we just don't have any sort of more intrinsic way of formulating any of the intermediate bits in the proof. And I'm not super optimistic in the sense that even for SDEs, one doesn't really have great ways of doing it intrinsically, manifolds, although maybe James can contradict me. And then, well, so one question is, so this was pretty much, the answer is certainly yes, but there's this remark that we saw that, you know, when you take that movie and you freeze it at a fixed instant of time, that actually looks precisely like sort of the Brownian motion on the manifold conditioned to come back to itself. And formally that should be the case. So there's a formal argument that you can make that tells you that this should be true. And okay, so we don't have a theorem yet that says that this formal argument works. And then, well, so there's a certain community where actually for, I suppose, 30 years now, they've in some sense been trying to construct this object using completely different techniques, so using theory of Dirichlet forms. And so you can build a Dirichlet form for that process, and then you can also show, I suppose, if you work a little bit, and it probably shouldn't be too hard, that the process that we construct has a generator which is an extension of the operator that corresponds to that Dirichlet form. And then you would like to say, oh, well, we have some sort of uniqueness statement in the sense that the process we construct is pretty much unique in a relatively large class of candidates, and these candidates are sort of the only reasonable candidates somehow. And so you would like to conclude from that this Dirichlet form generator has a unique Markov extension, and well, we have no clue how to do that. So that has been sort of an open problem for a long time. And it would be sort of nice also to, if you have SDEs, if you're not in an elliptic case, but in a sort of sub-Riemannian case, if you want, you have conditions for hyperellipticity. It would be sort of nice to figure out what's the analog here. Right? So there should be an analog of a Hermander condition or something like this that tells you something about smoothness of distributions for these objects. But okay, I think I stop here. Thank you very much.
Are there any questions? Remarks? Yeah.
How do appears the mysterious number 8 and 14?
Okay, so 14, it's all the so remember, in the SDE case, you had a counter term. If you take the Stratonovich interpretation, you had a counter term which somehow looked like that. Okay, so here, so then second order calculus becomes like fourth order calculus, and so you actually have to look at all the fourth order expressions you can make with the sigmas that are basically of this form. So for example, you can take expressions like, okay, so instead of writing it like this, I can write this sort of like this, where just the circle is just a placeholder for the sigma, and with implicitly summation over circles that have the same color. So I can look at things like this. So for example, covariant derivative in the direction of one of these sigmas of the covariant derivative in the direction of the covariant derivative of another sigma of that guy, for example. Right? So I can look at all possible multiple covariant derivatives that I can build that have 4 instances of sigma showing up that are sort of pairwise the same. Okay, so that comes from the sort of delta ij in the covariance of the noise. And then it turns out that there are exactly sort of 14 inequivalent expressions like that you can build. And the 8 came from the fact that if you impose that the gammas are the Levi-Civita connection for the metric for the sigmas, then it means that the covariant derivative of the metric itself is 0, and there's exactly one combination of these guys that doesn't involve the sigmas themselves, but actually only the metric, and which has a covariant derivative of the connection, of the metric, so that guy then disappears. And then I also imposed the fact that this guy is 0, and so all the guys that have this as a sub-picture, if you want, disappear as well, and there's 8 of them left. Okay, so that's the 8 and the 14.
Are there other questions? Yeah, Matt. No, yeah, sorry.
Are there any nice functions of the rubber band which give you martingales or super martingales?
Yeah, oh, well, nice, no. I don't know. Well, so you would think, so, well, I mean, you can formally write down the generator, right? So you have a formula for the generator, and then you can...
This links to my question, which would have been, do you have an ITER formula for that?
Well, okay, so here, now, the natural solution we build, at the end of the day, it just transforms normally under change of variables, right? So it's somehow more like Stratonovich, because it just... but you have something, I mean, in the sense that you can write down the generator, and so at least you have a conjecture of what sort of things give you martingales. Right? But, okay, so we haven't really proven that that formal generator is really the generator for the thing, but that shouldn't be too difficult. The other thing you can do is you can actually, so this we do it at some point in the proof because we need some injectivity or something, which is you can, you see, so you have the different terms, and so as a byproduct, one doesn't just make sense of the solution, so you sort of make sense of each term separately in the equation, right? And so then here it looks like this guy here, which in principle depends on the noise itself, where you can write it as this minus this minus this, and all of these terms only depend on the solution itself, right? And so you can ask yourself if, well, is there, right, and this guy here looks like it should be a kind of a martingale, right? Because it's a white noise times something, and so maybe that guy could be interpreted as a Wiener, as an E2 integral. Right? And so this is, so then you can ask yourself, we have some, well, this guy, you can make sense of it as an E2 integral because, this is just a continuous adapted process, and so you have an E2 integral. And then you can ask yourself, is that E2 integral actually a measurable function of the solution by sort of throwing all of this on the left-hand side and trying to make sense of each of these terms, and that is the case. So this you can prove that that's the case. So you can kind of extract, if you want, that term, which is a martingale of which you know the covariance, because the covariance is just that guy. You can extract it as a sort of explicit, to some extent, function of the solution by just throwing this on the left-hand side, and then you have to work a bit to interpret these things.
Yeah, there was another question.
Yeah. So, is the space of limit independent of the manifold on which there's also?
Well, I mean, the limit is a process that lives on that manifold, so of course it has to depend on the manifold. But right. Okay. So yes. So of course, if you're in lower dimensions, sometimes some of these things can also collapse. Right. So if you're in lower dimensions, then maybe that 14 becomes something less than 14, or the 8 becomes less than 8. Because some of these expressions that potentially could be different if you're in sort of high enough dimension end up being the same if you're in low enough dimension somehow. So for example, if you're in dimension 1 or something, then a lot of things collapse.
Yeah.
This 14-dimensional space, it's presumably not a linear space, is it?
Well, it depends what you mean by linear. I mean, of course, the solution as a subset of the solutions, of course not, because the solutions themselves, there's no way of adding two solutions, right? Because they are sort of processes with values in these loops in a manifold. As a space of equations, it's linear or affine, if you want, right? Because it just gives you, it just adds counter terms, and these counter terms are just linear combinations of constants. Right?
Yes, but there is no zero in that space. Otherwise, picking is.
That's right. So there's no natural zero in that space. Yeah. So it's, well, that's why I said it's affine, right?
Well, so what? Sorry. Yeah, David.
What determines the scale of the invariant Brownian bridge measure?
Oh, okay. Yeah. So you can still put a constant in here, right? You could kind of multiply. You could multiply this whole bit by a wait a second. So here you could just multiply these guys by a constant, right? So if you multiply these guys by a constant, then that would just change the scale.
But so, I mean, I thought maybe it was a different Brownian bridge at each point centered. If you move to another place in the manifold with different curvature, this is all taken into account.
Yeah. So there's the question of the distribution of the starting point of your Brownian bridge, and that's just at least the thing that should come out is that the distribution is, well, okay, so it's basically pt of xx is sort of the, the density of that distribution should just be the heat kernel, the diagonal of the heat kernel, right? Because then that's exactly the thing that makes your Brownian bridge invariant under, if you view your Brownian bridge as a random map from the circle into the manifold, you might want that measure to be invariant under rotations of the circle, right? And then there's only one measure for the starting point, which makes that. And that should be the correct one then.
The question? Yes.
So since you keep referring to the invariant measure, I'm assuming that you have some good reason to believe that there's a unique invariant measure to which you converge on the manifold?
Well, yes. Because we have, so this guy has good properties. So if we knew that the Brownian bridge is invariant for this guy, then that would immediately tell us that it's the unique invariant measure, and it would also immediately tell us that this guy has global. So right now you have the solutions, we only know they are local, so they might. The thing is, I didn't really assume anything on the manifold, so it doesn't even have to be compact. So the guy might just fly out to infinity in finite time or something, or even on a compact manifold, it might sort of roughen up in finite time and sort of explode in that sense. But if you knew that the Brownian bridge is invariant, that would immediately tell you that the solution is actually global, and you would also immediately get uniqueness. I mean, the uniqueness of the invariant measure is not immediate from what I told you, but we have some other results from which it would be more or less immediate.
So you don't have cases where on the manifold you just collapse at the point, or you have some singular...
Well, so you can't really collapse to a point because the noise sort of keeps on pushing against you collapsing, right? But you could, so what could in principle happen is, well, so first if the manifold, right, as I say, if it's not compact, you could kind of just fly away. But even if it, I mean, you could sort of roughen up, and of course you don't believe that, or you could somehow, you could create something that sort of starts wrapping around faster and faster, more and more, right? And you can't really rule that out. And so you could have this, I mean, you could have like a donut-shaped manifold, and then your circle might just sort of start wrapping around, have a piece of it that kind of starts wrapping around more and more. And then sort of like in finite time, it could kind of reach like infinite winding number, and then it would sort of explode. Right? So this we can't completely rule out. Of course, it doesn't happen. But.
Yeah, I think we can close now if there are no other questions. And thanks, Martin, again for this very nice lecture.